As seen in the previous section, simple linear regression is fantastic, but you have to take into consideration that there are some assumptions when it comes to the predictor, especially the probability distribution of the regression error. Just keep in mind that it needs to have a mean of 0, has an equal variance, is normal, and independent of the value of epsilon for any other observation. I recommend highly to read up on SLR assumptions to make sure that there's a reasonable chance that these assumptions hold in the population. Now in this section, I'm going to be talking about correlation coefficient of determination. Now there's a pretty nice long formula to calculate the Pearson correlation coefficient, and is shown on the screen. It is very lengthy, but can be done by hand. However, it's a little easier to understand when plotting a relationship between two variables on a scatter plot. To look at the correlation coefficient R. As can be seen over here on the figure on the right, positive correlation can be a weak, moderate, or strong uphill positive linear relationship. On the other hand, no correlation would be no relationship, no linear relationship. And last but not least, on the flip side of that argument, you can have a weak, moderate, or strong downhill linear relationship. And as can be seen here, these values can indicate whether it's a weak, moderate, or strong downhill linear relationship or weak, moderate, or strong uphill linear relationship. And we're talking about the strength of correlation. Now in Python, there is a correlation function dataframe.core, which calculates the pairwise correlation of the columns in the data frame and outputs a correlation matrix. On the other hand, in SciPy, the Pearson correlation coefficient can be measured between two datasets. There's also a calculation of the p-value, which relies on the assumption, just like I mentioned earlier in this section, that each dataset is normally distributed. And as also mentioned, those values vary between -1 and 0, implying no correlation. Now, if we look at the scatter plot that we generated in the previous section, and we were interested in determining the correlation matrix of our data set, one can do so by using the correlation function dataframe.core to calculate the pairwise correlation of the columns in the data frame and be able to output a correlation matrix. So let's go ahead and do that. But before I do, one would assume that it's going to be a positive number at more than likely moderate value. Perfect. So let's start. So first thing I need to do is import my pandas module. And second, I need to read my CSV file that I've stored locally on my machine. So I'm going to go ahead and copy some code that will allow me to determine the correlation of the columns in the data frame. So I'm going to be looking at my median income, and I'm going to be looking at my median house value. So based off of those two columns, I want to determine my correlation. So that's what I use over here. First, I enter my data frame or data, and then I use the .corr function to determine the value. Wonderful. So I was able to produce a 2x2 correlation matrix. And right off the bat, you can see here 0.688, 0.688, which shows positive correlation. Now, the next part, I want to also determine my Pearson correlation coefficient function, Pearson R in SciPy. So I'm going to go ahead and import my SciPy.stats as ST. And the next part, going to go ahead and paste to determine the Pearson correlation coefficient, Pearson R, of my data frames X and Y. All right. So right off the bat, we have the same value over here. That's fantastic, indicating a positive correlation. That's great. So now let's try to look at the other regression line that we plotted in the previous section. And to remind you, we created a plot of San Diego home prices from 2012 all the way to 2021. And if you remember, we were looking at the median sales price for the county. Now, if you remember, this is what the data set looked like. So one would expect that there is a strong positive correlation between the median sale price and time in San Diego. So let's put that to the test. So I'm going to go ahead and paste my code and attempt to determine my Pearson correlation coefficient, which takes in my data frames of X and Y. So in this case, my date time or my date time is my X and my Y is my sales price. Let's go ahead and try to run it. And as you can see, spot on, almost perfect positive correlation, 0.98. The highest value would be a 1. And my one-tail p-value at 1.89 to the power of negative 79. So a lot of times you would have to multiply that by 2 to determine your two-tailed p-value. And this factors in quite nicely a lot of times when we're looking at the significance level. Typically, your significance level is about 0.055%. So there is sufficient evidence that a positive linear relationship exists between sales price and date time. Great. So let's try to look at some other data sets that are out there. So one data set that we will be using is the stroke prediction dataset. Again, I'm going to be downloading from Kaggle. And I went ahead and copied some of the context here. And it says, according to the World Health Organization, stroke is the second leading cause of death globally. So there is a data set for us to predict whether a patient is likely to get a stroke based on input parameters, such as gender, age, diseases, smoking status. So as you can see here, these are the attributes that are available to us. So let's try to first read the CSV file that was downloaded locally and create a data frame called health. Right off the bat, as you can see here, these are the attributes mentioned: gender, age, hypertension, heart disease, ever married, work type, residence type, glucose levels, BMI, smoking, and stroke. Where stroke is a value of 1 if the patient had a stroke or 0 if not. So first things first, let's try to build a correlation matrix that will show us the correlation coefficients between pairs of variables. All right, so I'm gonna go ahead and paste some code, and I'm gonna again use my data frame health, and I'm gonna be looking at the following: stroke, age, hypertension, heart disease, ever married, smoking status, and glucose levels. And sure enough, here's my 1, 2, 3, 4, 5, 6 by 6 correlation matrix. So right off the bat, you can see that there's a correlation between age and BMI, albeit a weak one. And then there's a correlation of 0.23 between age and glucose level, and heart disease, hypertension, and stroke. Again, these are weak values when looking at the correlation coefficients between pairs of variables here. But as you can see, this is fantastic. Now in the next section, I would like to talk about the coefficient of determination. Now we have a lengthy equation, but The coefficient of determination, R squared, gives the ratio of the variance and the response variable explained by the predictor variable. So another way of determining this regression coefficient is to use the stats models package. So you have a OLS, response variable, predictor variable, then you use the data frame and try to fit it to give an output that includes this coefficient of determination. And we'll see after an example, see how this comes into play and how it is very handy. So I am going to first type from statsmodels.formula.api import OLS. OLS is the ordinary least squares, which is from the stats model regression package. Now, this is how easy it is. All you have to type is results equals OLS. Again, OLS, ordinary least squares. Now let's try to look at the response variable, heart disease, and age, in this case, will be my predictor variable. That's what it represents. We're going to be looking at my health data frame. And last but not least, type fit. Make sure to put equals versus minus, and then run it. Wonderful. Now let's look at the results summary. Right off the bat, you can see here your R squared value, which is 0.07, which is your explained variance divided by your total variance, which comes out to about 7% or so. The value of 4R squared means that only 7% of the variance in heart disease can be explained by the variance in age. Now, this low value for R squared suggests that age is not a good predictor for heart disease. Now, I was talking about explained and unexplained variance, and this can be obtained from the analysis of variance table, also known as ANOVA, that can be created by the following code. Fantastic. So you can see here, this is my explained variance. This is my residual. So when you sum up the explained variance plus the residual, you would get the total variance. So R squared is typically the explained variance divided by the total variance. So I'm just gonna go ahead and paste some quick code. And right as you can see, 6.96, which is over here shown as 0.07, 6.96% is your R squared. Of course, this is rounded, and this is how the value was calculated. So again, just to repeat, what we did over here is we created an ANOVA table for one or more fitted linear models in this case, where we're looking at age and heart disease. And as mentioned, the low value for R squared suggests that age is not a good predictor for heart disease based on that data set between those two variables. Great stuff. Now, if I wanted to confirm my results, best way to do it is with a scatter plot. So I'm going to go ahead and paste some quick code here, run it. And as you can see, when it comes to age and heart disease, age is not a very good predictor of heart disease for that data set. Now let's try to look at one more example and a different data set. In this case, it's the heart attack analysis and prediction data set. Again, this is from Kaggle. I'm gonna click on the following link. Now this is a data set for heart attack classification. There's a description, about this data set and its attributes. So what I'm going to go ahead and do is download and take a look at this data set. So I pasted the content here, and as you can see, we're looking at age, sex, exercise of induced angina, number of major vessels, resting blood pressure, maximum heart rate achieved, and if those are contributors to someone having a heart attack or less of a chance of a heart attack. So first things first, I'd like to take a look at the data set, read it, load into a data frame called health2. We have a few values here. Next step, I would like to create a correlation matrix by pasting the following code. Again, this is my data frame. I'm going to take a look at age, maximum heart rate achieved, cholesterol, fasting blood pressure. I'm sorry, this is the resting blood pressure, and this is the maximum heart rate achieved. And last but not least, if someone has a less chance or more chance of having a heart attack. So by scanning the correlation matrix, I see over here that there's a strong, or an indicator of a strong, or a moderate, actually, I should say, a moderate positive relationship between the maximum heart rate achieved and chance of a heart attack. Now, first things first, let's create a linear regression model to determine the ordinary least squares so that we can have a look at the R-square value. So I'm going to copy some code. And again, response variable is going to be my chance or risk of a heart attack. Over here, it's mentioned as target, and the predictor variable in this case is the maximum heart rate achieved. Excellent. Now, right off the bat, you can see here, we have a pretty high R-squared value, higher than the previous one and the other data set that we were taking a look at. To confirm, let's paste some code and determine the analysis of variance table. Right off the bat, we can see that we have the explained variance, we have the residual. So the total variance, again, is the explained variance plus the residual, and the R-square value is the explained variance divided by the total variance. So let's do quick code, copy and paste, and sure enough, almost 17.8% is our R-square value. Now this is higher than the 7% value, so this suggests that the maximum heart rate is a better predictor of a heart attack based on this data set, of course. Now, of course, I just want to mention I'm not a doctor. I'm just looking at the data, and especially the data set that I was able to download from Kaggle. But this is amazing. We're able to not only determine the coefficient of determination, we were able to also look at the skew, the kurtosis, and the residuals, the R-squared value. This is fantastic. Now, just like I did in the previous example, I would like to create a scatter plot. And I just want to make sure I have the right labels here. And sure enough, as you can see here, seems like it's conforming better with what we were talking about. And as you can see here, based on the fact that I decided to create a scatter plot of the heart rate and age, now between those two variables, there was a moderate downhole negative relationship. So that makes sense over here that it's pointing downward. But one can definitely modify the scatter plot to show the relationship between the variables. In this case, I was looking at the three variables. This is beautiful. And again, just to repeat, the coefficient of determination, R-squared, came in very handy, and it was able to provide us the percentage of data that is closest to that regression line. And of course, the further the data points are from that regression line, the less useful the line actually is in predicting the value of the response variable. This concludes our section on correlation and coefficient of determination.